Good afternoon, good evening, and good morning to you wherever you join us from. And welcome to this month's FISITA webinar featuring Mudassir Farooq from HORIBA MIRA. As I'm sure you know, HORIBA MIRA is a global provider of pioneering engineering, research and test services to the automotive, defence, aerospace and rail sectors. Its truly international team works in close collaboration with vehicle manufacturers and suppliers around the world, providing comprehensive support ranging from individual product tests to turnkey engineering, design, development and build programs. With over 70 years experience in developing some of the world's most iconic vehicles, HORIBA MIRA's engineers utilise the latest test facilities and simulation tools to make vehicles and journeys safer, cleaner, more efficient and rewarding. Their suite of 39 major test facilities, 100 kilometres specialised proving ground and wealth of engineering experience, combined with an expanding international presence, means they're confident about achieving their mission, which is that by 2020, every journey in the world will be positively influenced by HORIBA MIRA. Progress towards achieving this vision has been significantly advanced through the creation of the MIRA Technology Park. And tell me, this is Europe's largest transport technology R&D cluster. By applying advanced engineering and test validation capabilities to their customers' challenging programs, HORIBA MIRA is already shaping those journeys. Mudassir Farooq joined HORIBA MIRA as a graduate engineer 7 years ago, and since this time, he's progressed to become a senior engineer and has experience of working on various vehicle platforms from concept to post-production support. His work combines a mix of both simulation and physical testing, which gives him a broad perspective of the issues encountered at the early concept and design stage, as well as test-based verification and troubleshooting at the prototype stage. Mudassir is a chartered engineer with the Institute of Mechanical Engineers, has an MSc in Aerospace and Vehicle Design from Cranfield University and a BEng in Aerospace and Astronautics from Kingston University. Ladies and gentlemen, please welcome today's presentation live from the MIRA Technology Park in the UK, HORIBA MIRA Senior Engineer for NVH, Mr. Mudassir Farooq. Over to you, Mudassir.
Hello, everyone. I hope everyone can hear me. Thank you for the introduction. And so today's topic, tuning an exhaust for sound quality through subjective assessment of the CAE data. This is an internal research project that we undertook at MIRA to develop our own capabilities. Before I get into the details of the project and how we delivered it, I was just gonna go through a little about MIRA and what we do and where we're located. So as you've heard already, that we are an engineering service provider for transport and R&D services. Our three key elements of business at HORIBA MIRA is vehicle engineering consultancy, test engineering services, and a technology park. So we are located in the Midlands in UK, so at the heart of the British automotive industry, established in 1946, and we've got a technology park on site now, which houses 35 plus companies, and we've got a proving ground and other test facilities on site as well. To name some of these, well, you can see the test facilities that we've got. So this ranges from crash to EMC to brake, dynamics, NVH. So whole vehicle testing in essence. Some of our clients, so we are mainly based in UK, but we have got offices internationally as well, in China, in India, Brazil, North America. So we have international presence. And something recently that started off at MIRA is the MIRA Technology Institute, which was done through partnership with the Warwickshire College, Coventry University, Loughborough University, University of Leicester. So this is a facility on site that we have got over here, which allows us to deliver bespoke curriculum for OEMs, for universities, to develop the skill-based engineering required in the automotive sector. And we offer different courses all the way from apprenticeship to PhDs and master's degrees. We've got a short video about Mira, so we'll play that one first, and then we'll get to the project work. So guys, if you don't mind playing the video, please. Okay, so I guess everyone watched the video. Now I'm going to move on to the actual bit of the project that we did. So what is included in the presentation today? So I'll go through the introduction, so what aims and objectives that we set for ourselves in the beginning of this project, how we broke it down into different phases. So we've got 3 phases to go through, and then a conclusion at the end. Just to, before I begin, this project was done in partnership with FFT, which is a subsidiary of the MSc Softwares. So they help us with the CAE side of things through their software, FFT Actra. So, the aim. It was quite clear to us that we wanted to increase our vehicle development capability by conducting the sound quality development of the exhaust system at a CAE stage quite early on through subjectively developing it in the NVH simulator. So a lot of the times that we've seen in the past that development work happens at CAE stage where we cannot hear what the system sounds like. We do not have an appreciation, a subjective appreciation of the objective data. So this was the missing link here, and this was the gap we were trying to fill. So we set ourselves some objectives. So to name them, firstly, we needed to develop a procedure for ourselves for accurately measuring the source characteristics. So this means that for an exhaust system, the source will be the engine. So we had to identify the engine. to capture its effects. The second step was to create a process for conducting a CAE analysis of the exhaust system. This is trying to identify the metrics to define an exhaust system in a CAE model. Thirdly, to integrate that into our NVH simulator. I'll come to the NVH simulator a bit in detail later on. And then finally, to create a process for sound quality tuning of the exhaust CAE model through the simulator. So I'll go through each one of these in detail. Next slide. Going to go, before I begin, I'll go through some of the theory. I wasn't sure on the audience that might get over here, so I'm going to go through the NVH theory over here a little bit. So what we have in all its simplicity is an engine that's producing some noise, which is connected to an exhaust system, and that is radiating noise into the atmosphere. So what we will get is forward traveling waves, so incident waves, and then they will bounce back because of the geometry and the impedance of the air, and then you will have reflected waves. As a result of these two, you'll get a standing wave, and this is what we are solving for in an exhaust system. Just to explain a bit more about noise of a powertrain system, so engine or exhaust. Over here we've got a very traditional color plot, which is widely used in the NVH analysis. So what you will see on the x-axis is the frequency, and on the y-axis you will see the engine RPM, and the color represents the sound pressure level. And this is a recording at the driver's ear position. So what you see are these nice clear diagonal lines. Now, to explain what these are, in a normal engine, well, a four-stroke engine, let's say, you have one firing per cylinder in every 2 revolutions. So that means that we, in a 4-cylinder engine, which this is showing at the minute, for every revolution we get 2 firings. So as my engine RPM increases, my firing frequency increases, and it's a linear relationship between the two, and hence we get these diagonal lines. These are called the engine orders, and these are the harmonics of the engine orders. As an example, I'm going to play back noise for full vehicle interior noise. So this includes road noise, wind noise, powertrain noise, and so that was the engine, a vehicle revving through the RPM range all the way from idle to max RPM, and you could hear the engine, you could hear the wind noise picking up towards the end, and you could hear the road noise. Now, if I was to filter out the powertrain noise, so these diagonal lines, it will sound like this. So it's very tonal, very clear, distinct noise that you hear. So it gets rid of all the high frequency noise, the hushing noise from the wind and the road, rumble noise. So pure tones essentially. So that's what we're trying to tune over here, these orders. So moving on from there, the noise simulator. So the noise simulator essentially is we take some recordings on the track to create a model in this noise simulator, and then you can have a virtual model in a facility somewhere that you can replicate the load conditions, and it will reproduce the noise that we recorded. It's quite beneficial for target setting, for noise tuning, for development exercises, and for troubleshooting as well. And one of the aspects that it helps quite a lot is if you can imagine in an acoustic strategy where noise of the vehicle increases linearly with the engine speed. As you can see in the bottom right corner, you can just diagonal line, so it means as your vehicle increases speed, so does the engine order, and it's all linearly proportional. But it doesn't happen so much in the hybrid vehicles. So what will happen in a hybrid vehicle, you'll start off, the engine is switched off, you will roll under the battery power, so you'll go up to 20 or 30 kph, and then the engine will kick in, but rather than accelerating, the engine might stay at a constant speed. So the subjective assessment of such a behavior, it's quite, you can do it quite easily and clearly through a noise simulator. And that's one of the benefits of using a noise simulator. In our instance, what we've used the noise simulator is to tune the exhaust noise to apply filters and to identify what we want from this. So I'll explain a bit more later when through the project later on about noise simulator. So the three phases that we identified for the project. Phase one includes the baseline measurements where we identify, we take a snapshot of the vehicle. Phase two is to build a CE model of that, and phase three is the the tuning on the CE model. So going through phase one, baseline measurements. So for this, we chose a Ford Fiesta 3-cylinder petrol engine, 1 liter EcoBoost, and to build, we started off taking vehicle level data. So this is measuring on the track, so we get the road noise and the wind noise, and then we measured in the dyno, so we got all the powertrain noise contributions, and to build an NVH simulator model, we need loads at different conditions, tests at different conditions. So these are a finite number of conditions that when broken down and you put it back together and you make a simulated model of an infinite conditions. So we started off with the, like I said, the Fiesta, did the measurements and got our full vehicle data into the NVH simulator. So that's fairly basic stuff. The next one was measuring the transmission loss of the exhaust system. Now, how to quantify an exhaust system? One of the metrics used to, for this and widely used in the industry is the transmission loss of an exhaust system. And the technique used here was a 4-microphone test method. So you've got 2 microphones before and 2 microphones after, and you test under 2 conditions, a normal termination and an anechoic termination, or a near anechoic as you can get it to. And through the wave decomposition, you can work out what is your transmission loss. So in the plot in the bottom right, you see a transmission loss plot where on the y-axis is the transmission loss in dB, and on the x-axis is your frequencies. Transmission loss, the higher the better, so it means it's attenuating more noise. As you can see in low frequencies, it's not that bad, and as it goes higher in frequency, it's getting better and better in attenuating the noise. We did open up the exhaust just to see what was inside it, because this is from an OEM and we did not have any CAD data or any geometry, so we had to measure the exhaust system itself and get it into CAD. So one of the reasons that we did cut it open was to get the geometry for CAD and for the CAE. As you can see, it's got some fibrous wool, so we measured the properties of these wools as well. So that quantified my exhaust system. So the effort before this was, the test before this was to quantify a full vehicle. So that's a full vehicle. Now we did a component level test. And then finally, to get our baseline measurements complete, we needed to identify the engine noise source in terms of a source strength. So again, because we do not have the engine data, that means I was essentially treating the engine as a black box. I don't know what size of pistons or volume or pressure it was going through the pistons. So for me, and I'm not interested, I'm just interested what the engine produces. So I will treat that as a black box. So to get the engine noise, we characterize it in terms of its intensity and reflection coefficient. So in the block diagram you see on the top, what we did was we had two pressure sensors in line on the just before the exhaust system. So we can measure the incident wave and the reflected wave, and using the equations down here, we broke it down into intensity and the reflection coefficient. The tests were done under various loading conditions. So to capture the exhaust noise, to capture the engine noise accurately, we did the tests in a different gaze, under different throttle position, and revving through the RPM range. So this animated color map here shows you the different load conditions used, measured. So the intensity of noise gets higher and higher with the higher load input. So now at the end of phase 1, we have quantified our full vehicle interior noise through the simulator. We have got our component level noise through the transmission loss of the exhaust system, and we have identified our noise source. So that's all good. We've got a baseline set there. The next step was to get this into the CAE world, to build a CAE model. The software package we chose for this was the FFT Actron, as I mentioned earlier. So it's an acoustic solver, and what we analyzed over here was just the pure acoustic side of things. So this is not a vibroacoustic model at the minute. It doesn't include the shell radiated noise. We solely focused on the acoustically radiated noise here. Reasons for going with FFT Actron were, I'll come a bit later in the detail, but it was because of its capability to deal with the changes in temperature. Because of an exhaust system, you've got a lot of changes in temperature as you're revving up through the RPM, and a change in temperature indicates a change in speed of sound, and that will change your noise predictions. So what we did here was we got the CAD geometry that we measured of the exhaust into the CAE model. We replicated the perforates in the silencer boxes. We replicated the properties of the fibrous material in those back boxes, and then we ran a transmission loss analysis in the CAE world. And the plot on the bottom right, as you can see, is a transmission loss curve, the black one being the baseline measured, and the red one is the Actron, the CAE predicted one. So we have, as you can see, good correlation in the mid-frequency range from 300 up to 600 Hertz. The lower frequency range, the difference there could potentially be, and this is what we need to investigate a bit more, is probably down to the sound source that we've used for the measurement, that it might not have enough energy for it to generate the noise, and that's why it's showing a lot of attenuation of low frequency compared to CAE. The higher frequency, I'm not that worried about that region, because as the temperature increases, these peaks will shift to the right, and I'm mostly interested in the exhaust orders, which are low frequencies up to 500-700 Hertz anyways. So this is the exhaust correlation. This was done at cold conditions. So the test, the black line you see, was done at cold condition, and the CAE model representation is also in cold condition, which is room temperature. So I've got a CAE model in exhaust. It correlates well with the measured data. The next step was to get the effects of temperature and mass flow in the CAE for our prediction. So during our baseline measurements, we recorded the temperature and flow readings at these stations that you see on your pictures. So at 4 stations on the exhaust. So this is one before the mid box, one after mid box, and one before the back box and one after the back box. The good thing about Actron over here is we would feed the exhaust at this temperature, and it will, through its inbuilt solver, disperse this flow and heat temperature to that exhaust model. As you can imagine, we were testing for different load conditions, different gears, different throttle positions, and so for each one of them, it had to solve the temperature and flow analysis. So for instance, it would have to solve a single analysis for a second gear 100% throttle at 4,000 RPM, and the next step it would do is another 500 RPM, so at 4,500 RPM and 5,000. So it will start all the way from 1,000, go all the way to 6,000. So we had a few analysis to go through to get a full picture of the exhaust noise for different load conditions. So this is where it was coming in handy, where it was doing all of this analysis iteratively and then moving on to the actual acoustic solver as well. So the temperature and the flow results would be implemented on top of the acoustic mesh, and then it will be solved acoustically. So finally, to complete our CAE model correlation, we had to correlate the predicted noise at the exhaust orifice to the measured noise at the exhaust orifice, and also to do the prediction at the driver's ear position. So from Actron, we apply a unit load, and then we get a unit load output as a volume velocity at the exhaust orifice. And if you look at the plot on the bottom right of the vehicle, you can see in the front the engine noise source. So we identified that through our baseline measurements. The exhaust we got in there in the CAE model, and we're predicting the exhaust orifice noise, which you see as a dot right at the bottom right hand corner. And we have measured the transfer function from the exhaust orifice to the driver's ear position. So I combine all my results. So I use the source strength from the engine, I use the transfer function of the exhaust through CAE, and then I use the measured transfer function of the exhaust to the driver's ear position to predict my interior noise. And the plot on the bottom left, as you can see, it is a sound pressure level on the y-axis and the engine orders on the x-axis. The black line is the measured data and the red line is the CAE predicted data. This is exhaust noise contribution to the driver's ear position. And you can see that we have got good correlation. This plot is for a single load condition, but we've seen good correlation across the whole frequency band and different load conditions. Just for the purposes of this presentation, I'll just put this as an example here. So we have now completed our transformation into CAE model. So I've got baseline measurements and I've managed to transform it into a CAE model that correlates well with the measured data. So that's all good. Now I have my data my model in the virtual world. So what can we do with it right now? Which brings us to the sound quality tuning aspect of this project. Which is to phase 3. So for the exhaust noise tuning, what we did was we went back to the NVH simulator and we isolated the exhaust noise contribution, and we started to play with the filters to see what sort of noise we want to hear. So at this stage, we played the baseline exhaust noise and then we had some different filters applied on it. So each filter was to amplify a certain frequency or to attenuate another frequency. So we had a different combination in there, and this whole process went through a jury evaluation where we had the NVH engineers sit down and assess each noise, and we finally homed in on a target noise that we said that this is what we want to have from the exhaust noise. This is what we want to achieve after we've optimized it. So I'll play through the baseline exhaust noise first, and then the tuned one afterwards. So bear with me. So this first one is the baseline exhaust noise. Okay, and now I will play the tuned one. The difference is quite subtle, but it's more high frequency content in the tuned one compared to the baseline to give it that more of a sporty feel to it. And the filter looks like this curve on the top right corner that you see. So we've boosted a few frequencies, we've dropped the lower frequency, and essentially this filter has become our target line. So we know what we want now from baseline, but how to get there. So that is the next step. So we have a CE model, we can start to play with the CE model, and we have got a target noise as well. So this is where the optimization work and Actran played the biggest part here. So on the top right graphs that you see, so the top right one, you've got two lines, a red line and a blue line. And what we want to achieve is to get the red line down to the blue line. So this is blue, red is baseline, and the blue is the target where we want to be. And we have said to the software, to the optimization loop, saying, okay, we have a model, we can change a few parameters, and we've said, take the red and try to match the blue. These parameters one of them was the baffle position in the back box to move by about 10 centimeters. The other ones were change the size of the perforates on these baffles. And finally, it was the fibrous material properties, so to pack it, to make it more denser. The reason we went with these variables was because we didn't want to change the packaging requirements. So we didn't want to change the volume because of the packaging constraints that might be already there. So this was to show what we can do with minimalistic changes on the exhaust system. Can we meet our target? So we used an NLOpt, which is an open source optimizing algorithm software, combined with Actran, and we ran through our base model saying this is the target curve and these are the variables, and we've identified a band within which these variables can be moved. So after 200 odd iterations, it converged, almost converged to a complete solution. It couldn't match the lower exhaust target that we wanted, but that was mainly because that we didn't allow the software to increase the volume. So the lower frequency and transmission loss is dictated by volume of the silencers. So the bigger the volume, the more transmission loss you can get. But we didn't allow any volume change, so that's why it was struggling to meet that target. What I will do is I will play the target noise, which was the tune noise that you heard earlier, and then I will play the optimized noise as well. So first one is the target noise. Okay, then I'll go through the optimized version. So they both match, at least objectively. Objectively, again, the plot you see down here, where it's the black line is the tuned one, and then the red one is the optimized. We have got good correlation at this stage as well. So all in all, we managed to meet our targets of the optimized or the tune noise that we wanted. And so coming back to our objectives, did we develop a procedure for getting our sound source characterized? So yes, for the engine, it was quite critical for us to home in on this procedure because as an OEM, as a consultancy, we work for different OEMs and we will get benchmark vehicles, most of the data that we wouldn't have for engines. So getting GT power or a one-wave model of the engine would be a bit difficult. So for us to get it through measurements, that was a key part of this project, and that is something that we have got or we've managed to capture accurately. The next step was to create a process for conducting the CAE analysis in the exhaust system. So we got our exhaust model in the CAE world, and we managed to correlate the transmission loss between the two and also the predicted noise. Thirdly, we wanted to integrate our CAE predictions into the NVH simulators so we can play back the noise that we are generating through the CAE model. So it's no longer a line on a graph, it's we can subjectively tell the difference between the two, which one we prefer. So we've done that, and then finally we've got ourselves a process for tuning of the sound quality tuning of the CAE model based on our subjective assessments, based on the jury evaluation, and then running it through the optimization loop of the software. So all in all, quite a successful project it was, and that's it. Yeah, thank you very much for listening, everyone, and if you've got any questions, I will take them now.
Everyone else has and will as we embed this presentation into the area. Other questions from me around time frame. So this whole process you just talked through of establishing into this project and delivering these objectives, what was the time frame against that entire piece?
So you're just breaking up a bit. If I understood it properly, you were asking for the time frame, right? Okay. So since this was a research project, it sort of takes a lower priority when paid work comes in. So it slightly took a longer time than anticipated, but we completed this in a year and a half. Yes, there was quite a few hiccups in getting there in the first instance because we tried. So this you're seeing the final version here, which everything works, but going through the process, we went through a lot of trial and error. So we picked up on one method of measuring the engine noise for characterizing the engine noise, and it wasn't great, so we had to move on to this one. Similar with the exhaust modeling as well. So we had to try a few different softwares as well at this stage. So this is the final product right now.
Sound like a long time to me. Sounds like a good job well done. That's a fundamental part of the process. Over a while. Start to embed that. What next for this program? I mean, clearly, it becomes part of the plan with you guys, but what next for exhaust noise tuning?
Really sorry, I can't barely hear you there. Is it? Can you type?
Think about the next 10 years, some opportunities there, right?
The example here, an exhaust noise tuning, it was just as an example, we had to start off somewhere. So we picked an exhaust because it was slightly complicated than an intake system. So we thought, okay, if we can tackle an exhaust, we should be okay. The next step from here for us, at least, is we want to take it a step further. We go to the EVs, we go to a full vehicle. So this at the minute was just a component level exhaust. We want to go to a trim body level. We want to predict the road noise, do CE optimization on road noise and get it to the simulator and play it back. So yes, exhaust, you can treat it as an example, but there's a lot of other things that we can do with it, and the process was the main thing that was identified here, and the process will remain the same. It's just a different component, might require slightly different techniques for capturing the noise for those, but the process will remain the same.
Sounds like you've got at least another 18 months ahead of you, so well done everybody over there now. I'm sure it's going to give you much more flashbang and couple of months. Then got a bit of an audio challenge your end, so I'm going to say thanks for today. It's been an excellent insight into a really interesting project, and I'm sure people will draw from this presentation on the FISITA website for many months and years to come. So thanks for your time today, and I look forward to talking to you again.